Okay, so this is part 2 of section 5.3, and we're at the point where you get to try a couple practice problems. So there's 3 of them. Go ahead and pause it now, and then remember when you've got them all worked out, play it on and you'll see the answers. So go ahead and pause now. Okay, so for number 1, evaluate the integral. Well, this is really nothing more than a line. They're giving us the interval from 2 to 1, so that should look upside down to you. The smaller number should be on the bottom. So again, the 2 down here and the 1 up there, it should be flipped over. And we have to remember we put a minus sign out in front when we flip it over. So we're going to have the negative integral from 1 to 2 of this equation. And this really is just a line. So if I go ahead and look at the slide here, here's the solution. And if I went ahead and graph my line, we're really just looking at the interval from 1 to 2. So it's this area right in here between 1 and 2. Again, I guess I can highlight that. So if I just kind of shade it in through here, it's this area right in here. Okay, so what I decided to do first was kind of think of it as a trapezoid. This is a trapezoid where the bases are the parallel sides. So a formula for a trapezoid is 1/2 sum of the bases times the height. The height here would be going left-right, and that height is just 1. So my formula for area of a trapezoid, I have 1/2 the sum of the two bases times the height, which would be 1. And so the length of my two bases, if I plug 1 into my equation, 1 plus half of 1 is 3/2. If I plug 2 into my equation, 1 plus half of 2 is 2. And that's this height right here. Okay, so this side has length 2, this side has length 3/2, and I add them up and get my solution. Okay, second one. It gave me this integral, it gave me this function, and whoa, and it's asking me to find the average value of the function over the interval. And it says to use geometry as opposed to actually integrating it by hand. Okay, which is good because we don't have a lot of formulas to integrate, and this is a curve. So when I look at this equation, hopefully you can look at it and see that it's really just a circle that's been shifted and so forth. But if not, you could grab a calculator and graph it, and you would see that this is our parabola that we're looking at over here. So we're looking for the average value. That means the y-coordinate where a single rectangle drawn all the way across from -1 to 1 would be a certain height, and that height is f average. That's what we're looking for. So here's our formula, and our a and b, I'm going from -1 to 1. So b minus a, 1 minus -1, again -1 to 1 of our function. Now if I were to actually do this over on the side here, I'm not really supposed to just straight up find the integral. So this part in here, there is a way just to integrate it, but I'm supposed to be using geometry. So I'm thinking, gee, the area under the curve, I'll go ahead and highlight it one more time. I'm looking for this little space down here, and I'm looking for this little space in here. So how much area is there? Well, if I take the entire rectangle that goes from -1 to 1 in the x direction and 0 to 1 on the y direction, this entire rectangle, I would subtract off then a semicircle. This part in here is the semicircle. So area of a rectangle minus area of a semicircle. So the rectangle is 2 units wide and 1 unit tall, so 2 by 1. And then the semicircle has a radius of 1, so pi r squared. Cut it in half because it's a semicircle, not a circle. And again, the radius is 1. So simplify that and I get this. So this is how much area is underneath the curve in the interval we're looking at. And the definition of integral is area under the curve. So this integral, we've actually figured out what it's equal to by using geometry, and we plug that in. Now this 1 over 1 minus -1 becomes a half. We get our answer that way. Okay, oops, that's not what I wanted. Okay, next slide. Sorry, folks. Let's see if I can actually get this to move. Okay. So, for this one, it was just find the total shaded area, and they gave us the picture. Oh, you know what? Actually, I want to go back and look at the picture. So, here we go. So for this picture here, um, when I integrate, I'm finding the area between the curve and the x-axis. So if I take this equation that they're giving me for a parabola, and I just simply integrate it from 0 to 2, I'll get this area that's up here in the first quadrant. And then what I would get would be this almost triangular shape down here. And that's not the highlighted part. So I'm going to go ahead and integrate, instead of on the entire interval, I'm going to integrate from 0 to 1, and I'll get the area underneath the curve, or again between the curve and the x-axis. So I'll get this part up here. I'm going to call that region 1. And then all of this purple area that's down below that we're trying to figure out, again, kind of thinking about it geometry-wise, here's a large rectangle that is 9 by 2, going all the way around. So 9 by 2, that's 18 for the area of this entire section down here. But this part in here is not shaded in, so I would need to subtract that part off. And that goes from 1 to 2. So it's the area that's between the curve and the x-axis. So if I integrate from 1 to 2, I'll find how much this white space is. And I can subtract that off of the rectangle's area. So that's going to be my plan. So region 1, the part that's above the x-axis, is what I did first, I believe. So above x-axis, and then add it to the area below the x-axis. So integral of 0 to 1 of my function is going to give me the area above the x-axis. And then again, the area below, we said what we were going to do is look at the rectangle that was 9 by 2, and we're going to subtract off the piece that wasn't shaded in, which is the section between the curve and the x-axis. So it's the integral from 1 to 2 of the function. Again, we're kind of doing this ahead of time because really the fundamental theorem, basically how you evaluate this, doesn't come up until the following section. So I'm not sure why I chose to do it in this order. They might simply be expecting you to use your calculator to compute the integral. If you'd like to try that, you're welcome to do that. So for this part right here, I'm just going to do it on paper rather than calculator. So my antiderivative, this is going to be a 3x, and the antiderivative here, I add 1 to the exponent, it becomes x cubed, and I divide the existing coefficient by that new exponent, in this case a 3. So 3 over 3 is 1, and I'm going from 0 to 1. Area of the rectangle we said was 9 by 2. I'm looking for total area, so I'm going to put absolute values. I don't want that part that's down below the x-axis to be considered negative. Since it's total area, I want all the areas just added up, do absolute values of them. So again, we are already integrated, get the same thing over here. And then I'm supposed to go from 0 to 1 in this one, so I plug the top number in for both of the x's. So 3 times 1 minus 1 cubed, that's 2. Subtract, and then plug the bottom number in. So 3 times 0 minus 0 is 0. Again, we said absolute value of this, so it's 18 minus, and then this part here. So plug the top number in first. 3 times 2 minus 2 cubed is negative 2. Minus, and then plug the bottom number in. 3 times 1 minus 1 is 2. Okay, and then simplify. Well, that was the entire thing. It's a little longer today than usual. And hopefully that made sense to you. Let me know in class if you have questions.